blue.
Am I going the right, is this kind of, am I going the right way?
I think so.
So those are the reactants and then these are the products.
So then bonds.
Yeah, these are the total reactant bonds and then these are the total.
But then, because these should be like positive, right, though, because you're breaking them. So you have to put energy in.
Oh.
And when you make them, it's negative.
Oh, I got it backwards.
Yeah.
Okay.
But, yeah, this looks okay.
Okay. Thank you.
How's the rest of your class? All right, let's get started. Any questions before we begin? Is there anyone in here that's going to need to make up a lab or anything? Or needs to make up a lab? So your class has been pretty awesome of keeping up on assignments and everything. So just keep up the good work. So just get all assignments in. So check your grades too. I'm trying to catch up. I'm still behind on labs, but things should be entered in. So check your grades. I'm sure the percentages are off. I have to fix them because Blackboard doesn't calculate things correctly, but just make sure that everything's entered in, you're not missing assignments, all that good stuff. And then don't forget to register. So I know a lot of you can't register yet because you need a certain number of credits. But register when you can, especially if you're signing up for CHEM 105. I just want to know how many people are taking it or not. And if there's a large amount of people, maybe we could try to get an in-person lab section, but we'll see. Any other questions, comments, anything from yesterday that we need to go over? Oops.
Did you do a couple more examples of the redox?
Let's try this one. So potassium metal plus, trying to think of a good one. Plus iron nitrate. So try this one out. This might look a little odd. Let's see if you can determine. So we want to know who's being oxidized, who's being reduced. So did we determine either oxidation states and then who's getting oxidized, who's getting reduced? So let's look at this one. So let's just assign the oxidation states. So what's the oxidation state of potassium? 0. What's iron initially? In this one? So 3 plus. And then what is potassium in this case? And what about iron in our new product? So 1. And so now, who is being oxidized? So potassium, that's correct, so it goes from 0 to 1 plus, so it became more positive. And then we can say it's a reducing agent. And that makes sense, so it's the metals, so again, those metals tend to supply the electrons. And then which species was reduced here? So the iron, exactly. And so this was an interesting case. So you see this happening a lot where you might want to take a metal from a higher oxidation state to a lower oxidation state. And so I just made up some example, but this would be a typical reaction with potassium reducing some sort of metal. So nickel can do the same thing, you know, going from like 2 to 1 or 3 to 1, that sort of thing. Let's try another kind of weird looking example. So let's try this one. So you have this nitrate plus acid gives you nitrogen and water. So looking at this one, so this one, it's not really a full equation, so I should have added plus 10 electrons, but we don't really have an electron source. But what I really want to focus on is what's the oxidation state of nitrogen. So that's the only one changing in this little half reaction. So did we get a chance to look at nitrogen's oxidation states? So what's nitrogen in the reactant? What's its oxidation state? So it should be 0 for the product though, right? So elemental form, that one's 0. But for the nitrate, remember we have to use our other clues. So what can we use to help us figure out the nitrogen? That wouldn't help us here necessarily. We have this charge. So the swap trick works best if it's neutral. So the -1 charge kind of throws off our little swap trick.
So are you thinking of the nitrate as just the N and the O, or are you thinking of it as one molecule?
Yeah, so this is one molecule, right, the nitrate. You could draw it out as a structure, but it doesn't really help you that much. So nitrate has 24 electrons. So that's what nitrate looks like, but that doesn't quite help us for the oxidation states necessarily. But what do we know about oxygen? What's its oxidation state? -2. So it's always -2. And so now we can set up our algebra with this, which may help us. So now we have nitrogen, so we don't know what our oxidation state of nitrogen is. Then we have 3 oxygens times -2 equals -1. So then what's nitrogen? Keep trying. So you get -6 equals -1. So yeah, nitrogen equals 5. So nitrogen started off in the +5 oxidation state, and then it got reduced. It didn't tell us the source of electrons in this case. It could be some sort of metal, but all we really cared about was that it went from 5 to 0. So is that oxidizer reduced? Reduced. So it gained those electrons. Trying to see. Okay, let's do one more funny one. So this one might be tricky, but again, use what we know about oxygen and you might want your polyatomic for this HClO. So ClO should be some sort of polyatomic. So what do we get for the oxidation state of manganese in the reactants? 7. So that's good. So it sounds like we use the oxygen, so we know that's -2 times 4, and then plus whatever manganese is had to equal -1. So we got 7. And then what's chlorine on our reactant side? And we know oxygen's -2. So chlorine -1, oxygen -2. And then now let's look at our product side. So what's manganese on the product side? So 2 plus now. And so this chlorine's -1. But then what about this chlorine and HClO? So +1. And so how did you get that? Just walk me through.
Well, I knew that the hydrogen was going to be +1, and then the oxygen was -2, and so the way to balance it was just we're going to be +1.
Excellent. So that works out. So did everyone get +1 for the chlorine? So that was a little tricky in that one. We don't usually see chlorine in the +1 state. And so now we have to see, well, who got oxidized, who got reduced? And so who got reduced? So manganese, so it became more negative, gained electrons. And so therefore, who was oxidized? Chlorine. Do we want to do any more examples on this? Are we feeling better? Other thoughts? One more. Yeah, oops. So aluminum plus HCl gives you aluminum trichloride plus H2. So what do we get? What's the oxidation state of aluminum? 0. Hydrogen? Chlorine? Aluminum? And chlorine? And hydrogen? 0. Remember, back to its elemental form, back at 0. And so now let's answer, so who was reduced then? So hydrogen went from +1 to 0. And then who was oxidized? Aluminum. And that made sense. Metals supplying electrons became more positive. Let's look at one more example, because I forgot. We haven't looked at them in this form, but sometimes you could see a redox reaction abbreviated like this, where they're just really focusing on the metal oxidation states, so you don't even have to calculate anything. But take a minute or two looking at this. So who was reduced, who was oxidized?
Iron was oxidized.
So iron is oxidized, so losing electrons. And so who's reduced then? So cerium. Excellent. Any questions on the last one? There, or any of the other ones?
It's getting better.
Good. Just keep practicing. Is it just determining the oxidation states, which?
Yeah, I think I'm getting confused because I'm applying the subscripts and the coefficients and it's confusing me. Instead of just doing the charges.
Yeah. So just stick to the basics. Always go back to the basics. Your halogens should generally be -1. Your oxygen is -2. Hydrogen's always +1, again, unless those exceptions we mentioned. All right, so let's go back to exothermic, endothermic reactions. And so we left off last time, so we were calculating energy to make and break bonds, and kind of the key point, as we said, to break bonds, we have to put in energy, and so that's endothermic in itself, putting in energy. But then anytime we form those bonds, that was energetically favorable, so that drops the energy levels of the orbitals, and what that results in is energy coming out, so that's where the negative came from. And then we also learned, well, we can get our delta H of the reaction from this, or at least a really good guesstimate in the gas form, and this number tells us whether it's exothermic or endothermic. And so let's dive into that more now. And so these are just different energy diagrams to kind of show the flow of energy. And so now we're looking at an exothermic process. So remind yourself, so delta H then would be negative for exothermic, so heat is being released. So energy in the form of heat is released. And of course, all these exothermic reactions, right, they will feel hot to you. So you're feeling all that energy leaving. And so now let's look at the graph. So we're looking at this reaction. So carbon plus oxygen gives us carbon dioxide. On our y-axis, we have energy. So of course, energy just increases as you go up. And so it's saying for this exothermic reaction, that means the reactants are at a higher energy than the products. And so there's your energy difference. And so that would be related to your delta H. And so that change in energy is negative. So there's your energy being released. And so if the reactants have a lower internal energy than the products, the change in energy will be positive, and that's to these surroundings. And so this goes back to our first law of thermodynamics, so we can't just destroy or create energy, so it has to be transferred. So if our system then is becoming more negative, that means our surroundings get that same increase in energy, so that's what I'm saying when it feels hot. So now the hand is your surrounding, if you're holding a beaker of this reaction, and so that energy is going to be increasing as you feel that temperature. And system you could put on here, this is your reaction that you're monitoring, and surroundings is anything else. And so this is a really key diagram that you'll probably see a lot, especially if you continue in with chemistry courses. And so again, this is for an exothermic reaction, just emphasize that. And so exothermic, we said the products are lower than the reactants. Again, that delta H energy is being released. And so this is a reaction diagram that shows the progress of the reaction and the energy. And so what this is saying, so we have our reactants at their initial energy. Then we have this activation energy, so E act. And so this activation energy, it's whatever needed to get the reaction going. So this could be putting the reaction in some sort of transition state. So sometimes you have these kind of 5 bonded things. So if you do like methane and you're swapping it out for a chlorine. 1, 2, 3, 4, 5. Yeah, so you would have some weird transition state that's high energy, where you're basically about to lose this hydrogen and about to gain this chlorine or something like that, so some sort of transition state. And so your activation energy, that's whatever energy is needed to get you to that transition state. And then from there, it falls to the products. So in this case, again, our exothermic reaction, the products will be lower. And then the difference, so you notice that the delta H goes from reactants to products. So this difference would be equal to your delta heat of formation of the reaction. Yeah.
So this is what you were kind of saying about like the hand warmers, like the first activation energy, and then the reaction occurs, and then it falls kind of slowly to create products.
Yeah, exactly. So, right, you break it open, and I'm sure the activation energy must be pretty low for that iron oxide reaction. And then, yeah, if there's some sort of transition state where the oxygen's about to get onto the iron. And so the thing about the transition state is you don't always know what it looks like. So it depends whether you can measure this spectroscopically by some method. But yeah, just sometimes we know it, sometimes we don't, but some sort of high energy transition state. And then your products fall off as the iron oxide in the hand warmers. And as it makes that product, you're feeling that energy release. So if we compare the exothermic now to an endothermic process, so same initial diagram as before with energy increasing, except now our products are higher in energy. So that means we have to put energy into the system to get it to that higher energy. So you could look at the reverse reaction, so trying to split CO2 back into carbon and oxygen, so that's not as energetically favorable, so we have to put energy into the system. And so now, if we have, our reactants have a higher internal energy, so that energy has to come from somewhere, and so that energy is going to be coming from the surroundings. So now with their ice pack, now your hand is supplying that energy to dissolve the ammonium chloride. So let's just put up our example. Think ice pack and ammonium chloride dissolving. And so it's saying, so to do this dissolving, we have to put energy into the system. And so therefore that energy has to come from somewhere. We can't just create it. So the energy comes from the surroundings in the form of your hand or whatever muscle you're trying to ice down. And so the energy flows from the surroundings and then to the system. And so now their reaction diagram looks a little bit different. And so we have reactants, products. So again, products are higher in energy. So we still have our activation energy, although notice it goes from reactants to our transition states. So pretty high activation energy now comparatively. And that makes sense for those endothermic reactions. So now they're going to need a lot more heat, a lot more energy to get going. And then once it gets going, so again, not quite sure what that transition state would look like for dissolving ammonium chloride, some sort of rearrangement when they're about to split up is what I would imagine. And then products, so of course we can get our heat of formation again from the difference of products and reactants. And of course this time it is positive for the endothermic reaction. So key points, of course, just label the diagrams as well. So if you ever have to write an exam or diagram on your exam, so the key parts you need are just where are the reactants, where are the products. So obviously an endothermic one, the products should be higher. Exothermic, the products are lower. And then you would have to draw in your activation energy, your EA, so that would be reactants to your transition state. That's the highest point in your little reaction diagram. And then just make sure that delta H corresponds to the difference of products and reactants. We'll probably do, I think it might be on your homework. Any questions about these diagrams? So now let's discuss kinetics and what makes reactions go fast or slow. And so the speed of a chemical reaction is called its reaction rate. And this is something that you just have to measure, so you can't really predict it, but you can at least influence it. So the rate of a reaction is a measure of how fast the reaction makes products or uses reactants. And of course, if you were measuring this in a lab, you'd have to kind of figure out, well, which can I monitor, my products or my reactants? So that could depend on your technique, whether it's like NMR or if you have like a colored product, you could use spectrophotometry. And of course, the ability to at least somewhat control the speed of a chemical reaction is important, especially when you start thinking of things on an industrial scale. So of course, small scale, it doesn't matter as much if a reaction goes really fast. You're there in lab, you add a drop, it does a little explosion. That's cool. But then if you're thinking about that on the industrial scale, well, we can't just add a whole bunch and then create an exothermic reaction that's going to go out of control. So you have to think about, how do we control that reaction? Do we need to control the temperature? Do we need to control the rate of addition? What do we need to do? And so let's look at some factors that affect reaction rate. And this should be really tied to your lab that you're doing today. And so the first way you can change reaction rate is by changing the concentration. So in general, the greater the concentration, the faster the reaction, and that makes sense. So if you're just thinking about molecules in a beaker, if you have kind of 1 molar, you have fewer ions floating around versus a 2 molar versus a 3 molar. And obviously this is a very cartoonish representation of the molarities. But what you're thinking about, okay, if I have a greater concentration than of molecules, that means that the molecules have a greater probability of colliding with one another. And so that's the other thing about reactions, right? It depends on 2 molecules coming together. And so the more collisions you have, then the greater probability of making whatever you want to make. So greater concentration, greater frequency of collisions then. And so your concentration of gases is also another way to change it. And so if you have a higher pressure for gases, that also leads to a higher concentration. And so from this, if we think about the Haber-Bosch process, so we've looked at this reaction before. And so this is super important in industry, this reaction. So this is just nitrogen fixation to create ammonia, which is essential for fertilizer. And so this reaction occurs at extremely high temperatures and pressures, and it's not very favorable, so of course that's why they have to keep it at a very high pressure. So I'm not sure what pressure they use exactly, but I know that it is very high, so not ambient conditions. So that's just one example of how you can force your reaction. And then of course, with solutions, then it depends on your molarity. We haven't quite gotten to molarity. So molarity is just moles over liter, which is essentially just a concentration. So obviously the higher molarity, the more concentrated, and so the more particles there are to collide with and do a reaction. And so you saw this in lab comparing, or you will see it, the 1 molar, the 2 molar, and the 3 molar HCl plus the magnesium. So seeing that reaction rate and how it was dependent on those conditions. So of course another way we can change the reaction rate is temperature. So back to the Haber-Bosch process. So they also run this at an extremely high temperature. I want to say it's like 500 Celsius or something. It's like crazy ridiculous, the temperatures they use to get it to go. And so this is just kind of fun fact, and in general, for every 10 degrees rise in temperature, the speed of the reaction doubles. Again, this is kind of roughly speaking. And so all we want to think about is, of course, increased temperature gives us increased kinetic energy from those molecules moving around. And so if we have increase in kinetic energy, that means we can say our molecules are moving faster. And then, of course, if they're moving faster, that means more collisions. And not only more collisions, but also more productive collisions. And of course, what I mean by productive, so that would go back to kind of the activation energy concept, is that we have to hit a certain threshold for that reaction to occur. So it is possible for two molecules to just come along and then just kind of look at each other. And if they don't have enough energy to them, then they won't react. So then they'll just go on their merry way. But if you're at high temperatures, right, they're moving a lot faster. So then you have a higher probability of, yes, they're colliding. And then they would meet with the right energy to overcome the activation energy. So that's what I mean by productive collisions. So that collision will result in a new product. And so you'll also test this in lab, so comparing the reaction rates of cold bath versus a hot water bath. So now let's look at chemical equilibrium, how we can change things. So let's look at what is equilibrium. And so a good example of equilibrium is hemoglobin. So hemoglobin is a protein that's found in your red blood cells that reacts with O2. So of course this hemoglobin is iron-based. And so how it works, if we start in the lungs, that means that our hemoglobin is probably oxygen deficient, since it finished dropping off some oxygen somewhere in the body. And then if we look at this reaction, well, first let's understand what it's saying. So this little arrow here, the half double-headed arrow here, means that there's some sort of equilibrium. So anytime you see that, that means that the reaction can go backwards and forth. And so we'll see that too with like weak acids. And this will come up in our last chapter that we do. So anytime you see that, they can go backwards and forth, backwards and forth. And so now we're in the lungs, we're here. And so there would be a very low concentration of the complex hemoglobin. And so that means it would be favorable then in your lungs. The hemoglobin is going to go ahead, pick up some oxygen, so your lungs should be abundant with oxygen. Now it's created hemoglobin O2. So now that hemoglobin O2 goes around, and so now it goes down to your leg or something. And we can write this out. So hemoglobin O2. And so now thinking more of your leg or wherever it's going in your body. So now there is a very low concentration of O2 in your leg, right? Because your leg used that O2. And since there's a low concentration of oxygen, that's going to mean that the hemoglobin is going to disassociate, leave that oxygen in your leg or wherever it needs to go in your body. And now this hemoglobin will now return back to your lungs and, of course, repeat the process again. And so all that is just controlled by this equilibrium dynamics, and we'll later find out is related to Le Chatelier's principle. But we'll go back to what this is. And so let's do an arrow recap. So we've mainly been looking at this single-headed arrow. So this just means that we assume all reactant molecules are converted to product molecules in the end. And I'm going to bring up the strong acid example again. So with a strong acid, why we say it's strong is that it's completely disassociated. We use that single-headed arrow to show that no, we can't actually reform HCl in solution, versus our double-headed weak arrow, or excuse me, weak acid, double-headed equilibrium arrow. So again, HF, even though it is almost a substance I would never want to work with, it's considered a weak acid just because it reforms HF very readily. And of course, we'll learn this is also why fluoride salts can be dangerous. This is more kind of an aside, but if you're doing some sort of chemical reaction and you made fluoride salts, you'd have to be careful because you could be making HF, since that fluoride can go ahead and reform HF, so you'd want to neutralize that reaction. So that's something to be aware of. Whereas if you were working with a chloride salt, you wouldn't have to worry about that. You wouldn't ever reform HCl. And so now we have this equilibrium constant. And so the equilibrium constant basically tells us, well, how much to the product side or reactant side does our reaction favor? So this would something be calculated experimentally. So you would have to get some data or given some concentrations. And then let's look at the general formula for it. So we have some sort of A plus B gives us C and D. And so in this case, we would take it to the power of the coefficient. So products are always on top. So it's always products over reactants. And then this little letter indicates concentration. So it would generally be given in molarity. You could also use partial pressures. It's a very similar equation. It's just partial pressure and molarity are related, but there's also a factor to relate them. And so K would not have units, so it's just a constant. And so one thing that you would be asked to do is, for example, write an equilibrium expression. So let's go back to the general case. So we just are going to write our products, and we'll indicate that. So the concentration of C to the power of C then, so whatever coefficient we use to balance it, right? So these are just coefficients from balancing our equation. So it's to the power of whatever, then D to the power of the D coefficient over A to the power of the A coefficient times B, the power of B. Of course, you could continue on depending how many reactants and products you have. So looking at this, see if you could just write the K expression. What would that look like for this reaction? So what do we get for our expression?
So you just like add them all, so like I got N4O10 over N4O10.
So, and, oh, wait. Oh, you like added them?
Yeah.
So you wouldn't want to do that because we eventually want to plug in like concentrations. And we can do like a little sample. So all you do is you would take NO2 then to the power of 4, because that's what it is there. And then we would substitute in, again, a concentration later. And then you multiply it by the concentration of oxygen, and it's to the power of 1. You don't have to write 1. I'm just emphasizing that there's a 1 there. And then over N2O5 squared, since again there's a 2 there for a balanced reaction. So this is what it should look like.
So the coefficient, remember that's out in front, that goes into the exponent?
Yeah. Yeah, so why it gets exponented is now we're saying, so for every 2 equivalents that we consume of the N2O5, we're making 4 NO2, so that's going to be exponentially increasing compared to this decreasing. And so some example then of what you would do with this, or what you would be asked to do. So then you might say, like, what is the equilibrium constant? If the final reaction concentrations were as follows. And so you have to measure K too once the reaction is kind of equilibrated and steadied itself. So, you know, you initially do a reaction, and then it might be going back and forth initially until you get to kind of what's called that equilibrium state, where your forward and your backwards reaction are the same and basically nothing's changing. And so then let's say, so our NO2 concentration is 0.3 molarity, our O2 is 0.5 molarity, and the N2O5 is 0.2 molarity. And so what you would do is you would just plug these concentration values into this expression that you found. So now plug into expression. So you have your K equals, so now take your concentration value for NO2. So in this case, 0.3 to the power of 4 times oxygen, so 0.5 divided by our 0.2 squared. So then you set that all up, then you'd have to plug it in your calculator. So 0.3 to the power of 4 times 0.5 divided by 0.2 squared. And so that just spits out your number, and then that's just your K, so your equilibrium constant. So for this random example, our K is about 0.1. And so now let's kind of answer, well, what the heck does this number even mean now? And so what does the value of K imply when its value is greater than 1? And so again, that's why I say just generalize products over reactants. And so if our value of K is greater than 1, which side is it favoring? Our products or our reactants? So greater than 1, it's reactant products over reactants. So it should be products, right? So if you have a large amount of products, so you have some sort of great concentration, you have a number greater than 1, so that must mean that there's more products than reactants. So you can say that it favors products. And so this reaction is just one example of the equilibrium constant favoring the product. So in this case, you have hydrogen plus bromine reacts to give you hydrobromic acid here. And so apparently the K equilibrium value, when it's calculated, is a large number. And so if it's a large number, again, that's telling us that it's favoring the products in this case. So products go on top with our expression, so it's going to be favoring the products there. And so the real K value for this one, just so you can get a sense, is 1.9 times 10 to the 19th. So of course that's really large, really favoring the products there. So you probably wouldn't expect very much concentration of H2 and bromine at all. So then what happens then if K is less than 1? What's favored? So reactants now. And so now looking at this example of nitrogen plus oxygen gives us NO gas. And so the equilibrium constant, so let's look at what it actually is. So 4.1 times 10 to the negative 31. So that's extremely small. And so that means that, right, not very much products are being formed. And then this also makes sense. So can you imagine if the nitrogen and oxygen in the air favored making NO? There would be no oxygen left for you to breathe. So that makes sense that this reaction is not very favorable. So there's only very small amounts of NO in, of course, the atmosphere. So how does this relate to Le Chatelier's principle? And so let's look at this. So once a reaction is at equilibrium, the concentrations of all the products and the reactants remain the same. So all that's saying, they're not saying that they're equal or anything. It's just saying that whatever the final concentration that you have, that's going to be your product concentration and your reactants. And so that will be the same. However, if the conditions are changed, then the concentration of the chemicals will all change until equilibrium is restored. And just remind yourself, so K is the same. So K should never change, right? That's your equilibrium constant for any sort of reaction. So if you go back to this NO reaction, for example, the equilibrium constant is always this answer. So it doesn't matter what your starting concentrations of, as long as it's at equilibrium, you'll plug in the values and it should give you that number back, if it was, of course, an accurate problem. And so all this is saying then is our concentrations could be different, and we'll see what this means. So we may be perturbing the system by adding more starting material, so then obviously all the reactant concentrations will change. But again, your equilibrium constant will be the same. And it says unless you change the temperature. So that's the only way you change the constant. So as long as you're at that same temperature, same constant. All right, so let's look at the picture first before we try to decipher all those words. And so I like this graphical representation here. So we're looking back to this, it's a different reaction now. So the dimerization of N2O4 and it becoming undimerized to make nitrogen dioxide. So just going back and forth. And so initially we're at equilibrium. So we have whatever our initial concentration of NO is versus N2O4. And so notice there's a spike here. And so we've disturbed the equilibrium by adding more NO2. And so before we get confused, so this Q is just a snapshot of the reaction. And it's the same formula as K, though. So all that's saying, so if we go back to our formula for what K was, so Q is the same form, it's just that it's not at equilibrium. So Q is just our snapshot. So we still plug in, we still do the same thing, raising it to the power of the appropriate coefficients. It's just Q is, we're looking at it at just a certain point of time, so it may not match K. And so we've disturbed the equilibrium, we've added more NO2. And so what it's telling us mathematically is Q is greater than K. And so let's think about that for a second. So products over reactants. And so if Q is greater than K, so that must mean that we have more products than our equilibrium concentration of products. And so that's what's happened here, right? It makes sense with our graph. So we've added more of the nitrogen dioxide, which is our product. So we artificially perturbed it. And so now it's going to try to go back to equilibrium. And so to accomplish that, so we perturbed the system by adding too much NO2. And so now by Le Chatelier's principle, it's going to fix that by favoring the reverse direction initially. So now it's going to be forced to go backwards and dimerize. And we see that here on our chart. So now we perturbed it. So now that means we're going to start making more dimerization. And then now here, equilibrium is reestablished. All that means is that our K is back to being K. But notice that the concentrations are different from our initial concentration. So we added a bunch of NO2. And so even though we consumed some of that NO2 to make more of our dimer, there's still, of course, more NO2. And then same thing with our N2O4. So we created more N2O4 now with our system. But again, it's at equilibrium because our K value would match. So let's try to look now at the words. We'll go back to the words. So let's look at this example before we look at words, because the words get messy. And so in this one, all we did now was we added reactants formally, so we added more N2O4, disturbed the equilibrium. And so if we added more reactants, now our Q is less than K. So products, reactants. Okay, now we have too many reactants essentially. And so now we're going to force the reaction to the right, to the product side. And so we see that reflected here. And so our new equilibrium is established. And the N2O4, of course, decreases as it gets converted to our product. So now let's go back to the words. And so let's start with adding reactants. So we can still think of our N2O4 for now and our dimer. And so it says a reactant is added. So how does it change the equilibrium? So a couple of things is that a reactant will change the concentration as long as it's an aqueous solution or it's a gas. And so that is as long as it's not a solid or a liquid. So what this is saying is, let's say you had, if we go back to our carbon plus oxygen gives us CO2. So if we were looking at this, if you just had a pile of carbon, since that's what carbon is, so adding more carbon, so adding a greater pile of carbon would not help your reaction right here. And so this is kind of odd because this reaction would only depend on the concentration of CO2 then and O2, since these are the only ones in the gas phase. And then carbon's a solid, so it would not matter. So it doesn't matter how much solid we add, it's only going to be based on those surface reaction, so it doesn't increase our concentration and doesn't change anything, so it's not included in the equilibrium expression. So solids and liquids not in equilibrium. And so the liquid could be, water, or if you were doing what's called like a neat reaction, where you add your liquid reagent to it and it's not diluted, then that's just neat, so that would not be included in the expression. And so again, adding reactants, how will it affect it? So as long as it's included in the equilibrium expression, the reaction will proceed to the right, so we saw that. And so again, it increases the rate of the forward reaction and should have no initial effect on the reverse reaction. and it goes until the right until equilibrium is restored. And so we mentioned at our new equilibrium position, we have more of the products than before, less of the non-added reactants, but of course, less of the added reactants. And so all that was saying is, okay, we added more products, so now we have less than what we added, because obviously some of these reactants became products over here. So what happens if you remove a reactant? Now we'll go back, so N2O4, looking at this reaction. So if we remove our reactant, which way do you think that's going to drive the reaction? To the left, exactly. So if we take away some of the reactant, well, now we need to get back to equilibrium. So that means that our products are going to go backwards and make more reactants. So again, reactant removed, then now it goes in the reverse direction, proceeds to the left to replace that removed N2O4 until we get back to our equilibrium. And so initially, removing the reactant decreases the rate of the forward reaction, and then the reaction goes faster in reverse. And so at our new equilibrium position, obviously we'll have less products than we started of, and more. If we had some sort of other reactant that was not removed, we would have more of that, and of course more N2O4 was formed. And of course K would not be affected, so it should be the same K once it's back at equilibrium. And so changing concentration, so again, adding a reactant will decrease the amount of other reactants, so it's going to consume the reactant. So let's just look at this general A plus B gives you C plus D. So if we added a bunch of A, so if we added A, that means more B would be consumed, and the reaction would be pushed forward towards the product side. So sorry, I should have drawn it as equilibrium. So add A, so in consequence, B is consumed, or more B is consumed, and of course C and D produced. And of course, you can also remove a product to also increase the amount of other products. And I know I've mentioned, at least I think I've mentioned it before. I mentioned a Dean-Stark reaction in here, right? Maybe. I'll pull up the picture. And so this is really useful. So this is a Dean-Stark. And so what this is saying, so removing a product will increase the amounts of the other products and decrease the amount of reactions. And so sometimes what this is really relevant for is, let's say you have some sort of A plus B gives us C plus H2O. So this would be a condensation reaction where you're forming water. And so this is a common reaction, but if you want to drive it forward, you can use Le Chatelier's principles to help you. And so if you remove a product, so in this case you can remove water, and that's what this little Dean-Stark apparatus does, is you're boiling your reaction here, all the liquid travels up into here, and then you end up with your layer, so you would have water and then your less dense organic solvent on top. And so your water eventually collects, and notice your organic solvent would go back in since it's on top. But then, so this is removing the water from our reaction here. So that's removing it, and then it would keep driving that reaction forward. And then the cool thing about the Dean Stark, at least if you have a fancy one, like in this little picture, is you have this stopcock, so you could drain out the water. Let's say you had a lot of water being removed, so you drain it and then just keep going, keep driving that reaction forward. So that's really useful. And so that's how you use that in real chemistry. And so again, equilibrium shifts away from the side with added chemicals or towards the side with removed chemicals. So all that's saying is if you add A or B, that's going to force it to make more products. You could remove C and D. Obviously, that forced it to make more products. But then if you removed A or B, so now I'd want to make more A and B. So shifting C and D back towards the products. So you could also add products. So if you added C and D, of course, that would drive it back to the reactants A and D. Blah, blah, blah. Oh, okay, so I forgot one little point in here with Le Chatelier's principle. And so kind of the key thing with Le Chatelier's principle is it still applies to endothermic and exothermic reactions. So with endothermic, let's say you have A plus B plus heat then. So you could treat heat like a reactant, and then that gives you C plus D. So if you have an endothermic reaction, and if you remove heat from it, right, that would not be favorable. So if you remove heat, then you would cause it to shift backwards. So then it would go back to make more heat. Meanwhile, if you wanted to drive it forward, you of course could add heat. Adding heat would be like adding a reactant. It would drive it forward. Meanwhile, exothermic is the opposite. So we can treat heat like a product. So if you had an exothermic reaction and you added heat to it, so now that would drive the reaction backwards and drive it back to form A plus B. And you could cool it down, and that might cause it to go faster. So you cool it down, remove heat. That would cause A plus B then to be favorable. So this should help you with your lab, so then you can look at the last part where you're looking at your iron reaction. So iron plus the thiocyanate to give you, now I forgot what oxidation state iron was in. Is it iron 1, iron 2? So you make this product, right? And then you have to determine, well, is it endothermic or is it exothermic based off of what happened when you heated it. So if you heated it, did it go lighter? Did it go darker? Which way did it shift it? So that should help you for that one. All right, let's quickly talk about catalysts really quickly. I know we're almost out of time. So catalysts are really cool in that they really change the entire mechanism and provide a new pathway. So they're any substance that affect the rate of reaction without being consumed. And most catalysts, we just consider them to increase the reaction rate. Technically, it could decrease it, but generally those would be called an inhibitor. So an inhibitor is kind of a subset of catalysts that would do the opposite and slow your reaction down. And so catalysts are generally consumed and then reformed later, so you can recover your catalysts. At least you should be able to. And so what's really key is this little diagram here. And so the blue is our uncatalyzed pathway. And so notice, right, the blue has a very large activation energy. But then catalysts work by providing a whole new pathway. And so they're really creating, another transition state, or just like a lock and key mechanism you can think of, where something can bind and then it's primed in the right position in the correct orientation. And so this transition state, whatever it does, it goes through two little mechanisms, hence why it has two little humps here. But then notice, right, the activation energy on both those pathways is a lot smaller. So this is much more favorable, and so that is our energy diagram for our uncatalyzed pathway. And so it doesn't necessarily have to have two humps, but again, just emphasizing it's going through a completely different pathway. And so there's different types of catalysts too. So a homogeneous catalyst would be all species are in the same phase. And so the easiest thing would be think of like an aqueous catalyst. So you have some sort of catalyst in solution, add your reaction to it, also in solution, do something. And then heterogeneous, this would be like your car. So your car has a catalytic converter, and that is just some sort of solid piece of metal. And then, of course, the reactants pass over in the gas phase and bind appropriately. I know we're basically out of time, but I just wanted to show you. So there's a really famous class of catalysts called these olefin metathesis catalysts, and they're kind of called the Grubbs catalysts. And they catalyze this reaction of olefin metathesis, so you can see they're like swapping groups around. But again, I just want to emphasize it's creating a whole new pathway. So these molecules basically bind these starting materials to them, and then they're able to kind of rearrange the bonds by, again, providing a whole new way using these metal catalysts. All right, so I think we have to end there because of time. And I will see some of you in lab in 10 minutes. Oh, I do have quizzes. I graded your quizzes, so if you want them, hand them to you. And I have homework printed in lab, so you can grab it in lab. I know. And then it looks like really dark outside.
Yeah, like, are we supposed to be in bed? Pretty sure.
Here, come get your quizzes. Sorry, my legs are free.
She just gave it back to me. Thank you.
Yeah.
Let's go. Yeah, my part was the one.
Oh, homework.
And then I have one more homework assignment.
Sweet.
Thank you. These
Oh.
are from last week.
Thank you.
Oh, I think that's.
Wait. It was weird because at first it switched stuff. Because I was like, wait, and then the number didn't look right. So,
Yeah, that's what I did too.
yeah, so I switched it. Like,
You too.
I don't know how I got.
Oh, but I'm seeing you Friday, right?
Oh, Friday, right.
Yeah.
Okay, thank you.
I'll try to send, I still need to send a calendar invite. I'll probably do that just for me. I'll try to do that like right now.
Okay, that's in
yeah,
first grade.
that's where I put that.
Where?
In first grade.
Yeah.
Okay, cool.